Standing outside on a clear night, you look up at the familiar patterns of stars that have marked the sky since childhood. And most of the constellations appear exactly where you expect them to be. Cassiopeia traces its distinctive W across the northern sky, and Orion stands proudly in the winter heavens, and the Big Dipper points toward the North Star, just as it always has. But something has changed in the autumn sky, something that would be immediately obvious to anyone who remembers photographs of the night sky from centuries past. Andromeda hangs in its usual location among the constellations of Perseus and Cassiopeia, but it no longer appears as the faint smudge that required dark skies and keen eyes to spot. The galaxy now shows itself clearly to anyone who looks up, appearing as a distinct spiral disk roughly 3 to 4 times the diameter of the full moon. You can see the spiral structure with your naked eyes, if the sky is dark enough, faint arms curving outward from a brighter central region that glows softly against the background stars. The overall light from the galaxy is not bright enough to cast shadows or to make reading possible, but it provides enough illumination to see your hand if you hold it up against that part of the sky. This is Andromeda, approximately 1.5 billion years from now, and what you are witnessing is the beginning of a process that will transform both galaxies over the next several billion years. You are listening to the Drowsy Astronaut, and tonight we are going to witness the entire merger of the Milky Way and Andromeda galaxies as experienced from Earth's surface across billions of years of cosmic time. This will be a slow and unhurried journey through deep time, watching the night sky gradually transform as 2 spiral galaxies approach each other, interact, and eventually blend into a single system. If you are still awake later, feel free to share in the comments where you are listening from tonight. Now let's return to the sky above you and understand what this enlarged Andromeda means. The galaxy's increased size tells you that the distance between the Milky Way and Andromeda has decreased substantially since the present day, and the apparent size of an object in the sky depends directly on how far away it is. Andromeda currently sits about 2.5 million light-years from Earth, a distance so vast that light from the galaxy takes 2.5 million years to reach us. The light you see when you look at Andromeda today left that galaxy before humans existed, before our genus Homo appeared, when our distant ancestors were still primitive primates. But the galaxy you are looking at now is closer, and the distance has shrunk to roughly half its current value. Looking at Andromeda's disk spread across the sky, you can estimate that the galaxy now lies approximately 1.2 to 1.3 million light-years away, and this reduced distance makes it appear about 4 times larger in angular size than it does in the 21st century. The brightness has also increased because the same amount of light is now spread over a larger area of your retina, and the concentration of that light makes the galaxy clearly visible even from suburban skies with moderate light pollution. The spiral arms are faint but discernible, curving outward from the core in elegant sweeps that reveal the galaxy's rotation and structure. The Milky Way band still arcs across the sky overhead, stretching from horizon to horizon in a glowing river of combined starlight from billions of stars in our own galaxy's disk. Our Sun orbits the center of the Milky Way at a distance of about 26,000 light-years, positioned roughly halfway out from the core to the outer edge of the spiral disk. When you look at the Milky Way band, you are looking through the thickness of the galactic disk, seeing thousands of light-years of stars layered in depth. When you look at Andromeda, you are seeing another galaxy from outside, viewing its entire structure from a distance. The two galaxies are approaching each other at a speed of about 110 kilometers per second, as measured from the present day, and this velocity represents the mutual gravitational attraction between two massive objects separated by cosmic distances. Gravity pulls everything toward everything else, and the strength of that pull depends on mass and distance. Both the Milky Way and Andromeda are massive galaxies containing hundreds of billions of stars, plus dark matter halos that extend far beyond the visible edges. And the combined mass creates a gravitational pull that has been drawing the galaxies together for billions of years. Standing here, 1.5 billion years from now, you are witnessing the visible result of that mutual attraction. And the approach has been gradual and continuous throughout all the intervening time. The galaxy has been growing larger in Earth's sky generation after generation, century after century, millennium after millennium. The change from year to year would be imperceptible to human eyes, but over spans of millions of years, the growth becomes obvious when comparing observations. By the time you arrive at this moment, the difference from the present day is unmistakable. The night sky around Andromeda shows stars from our own Milky Way scattered across the view. Foreground stars that happen to lie in the same direction as the distant galaxy. Some of these stars are bright and prominent, while others are faint and barely visible. None of these foreground stars have anything to do with Andromeda itself, and they sit at distances ranging from a few light years to tens of thousands of light years from Earth. Andromeda lies far beyond all of them, separated by a gap of over 1 million light years that contains almost no visible matter. Looking toward other parts of the sky, you see that most constellations have changed their shapes over the 1.5 billion years that have passed since the present day. Stars move through space in their orbits around the galactic center, and these motions gradually shift the apparent positions of stars as seen from Earth. The constellations that seemed permanent to human observers across millennia are actually temporary patterns, and given enough time, they dissolve and reform into different configurations. Orion no longer looks quite like Orion, and the Big Dipper has been distorted into a different shape. But despite these changes to the detailed patterns, the overall character of the night sky remains familiar, and the Milky Way band still dominates the view in dark locations away from artificial lights. The Sun continues shining as a main sequence star, and Earth continues orbiting the Sun in the same orbit it has followed for billions of years. The solar system is stable and undisturbed by the approaching galaxy, and life on Earth, if it still exists in forms we would recognize, continues under skies that are only slightly different from those known throughout human history. The major change is Andromeda's increased size, a clear indication that something momentous is underway. The galaxy's spiral structure, visible in the sky, tells you about Andromeda's shape and orientation as seen from our perspective. And the view shows the galaxy tilted at an angle rather than face-on or perfectly edged on. You can see the central bulge where the core region concentrates billions of older stars in a dense spherical distribution. The spiral arms extend outward from this core, and they appear brighter in some regions where young hot stars and star-forming nebulae add their light to the overall glow. The outer edges of the visible disk fade gradually into darkness, and beyond the visible light lies an extended dark matter halo that cannot be seen directly. Andromeda contains approximately 1 trillion stars, according to current estimates, making it roughly 4 times more massive in stellar content than the Milky Way's estimated 250 billion stars. This size difference means that when the galaxies eventually merge, Andromeda will contribute the majority of the stars to the final combined system. The dark matter halos of both galaxies are even more massive than their visible stellar components, and the dark matter extends far beyond the visible edges and plays a crucial role in the gravitational interactions that will shape the merger. The time until the galaxies make their first close approach is still measured in billions of years from this point, 1.5 billion years in the future, and the merger will not happen quickly or suddenly. You are watching the early stages of a process that will unfold over several billion more years, with multiple passes and interactions before the final blending is complete. The approach is patient and inexorable, driven by gravity operating across vast distances at a pace that seems slow even on cosmic timescales, but which is nevertheless continuous and unavoidable. Looking at the enlarged Andromeda hanging in the autumn sky, you can think about what this means for the future and what will happen as the approach continues. The galaxy will grow larger and larger in the sky over the coming billions of years, and eventually it will become the dominant feature of the night sky, rivaling or exceeding the Milky Way band in prominence. The two galaxies will interact gravitationally, distorting each other's shapes and pulling stars and gas between them. They will pass through each other at least once, possibly twice, before their cores finally merge and the two systems become one. The merger is inevitable, and the only uncertainties involve the exact details of timing and the specific orbital parameters that will determine how the galaxies approach and interact. Computer simulations of galaxy mergers suggest various possible outcomes depending on the precise angles and velocities involved. But all simulations agree that the end result will be a single giant elliptical galaxy containing the combined stellar populations of both original spirals. The spiral structures will be destroyed during the interactions, and the stars will be redistributed into a three-dimensional ellipsoidal shape, rather than remaining in flat, rotating disks. Standing under this sky, with Andromeda clearly visible overhead, you are at the beginning of that story, and over the journey through the next several parts, you will watch the entire process unfold. The night sky you see now, with its familiar Milky Way band and its enlarged neighbor galaxy, represents the calm before the interactions begin. Time will continue to pass, Andromeda will continue to approach, and the sky will continue to change in response to the gravitational forces reshaping these massive systems. The night sky has transformed over the hundreds of millions of years that have passed since you last looked up, and time has advanced from 1.5 billion years in the future to roughly 2.5 to 3 billion years ahead of the present day. Andromeda now spans an enormous section of the sky, and its apparent size has grown to 20 or 30 times the diameter of the full moon. The galaxy dominates the autumn heavens in a way that would have been unimaginable in earlier epochs, and its light contributes noticeably to the overall brightness of the night when the moon is not present. The spiral structure is clearly visible in exquisite detail, and you can see the bright core region surrounded by curving arms that extend outward in elegant spirals. Individual bright patches are visible within the arms, and these represent massive star-forming regions or young star clusters that shine with the combined light of millions of hot blue-white stars. The dust lanes that line the inner edges of the spiral arms appear as dark bands cutting through the lighter regions, and the contrast between bright and dark areas creates a three-dimensional appearance that makes the galaxy seem almost close enough to touch. Looking at the galaxy's orientation, you see that it appears tilted at an angle, and you are viewing it from a perspective that shows both its disk structure and hints of its depth. The spiral lies neither perfectly face-on nor perfectly edge-on, and this intermediate angle allows you to appreciate both the spiral pattern and the thickness of the galactic disk. The far side of the galaxy appears slightly dimmed compared to the near side due to the additional distance and the intervening dust within Andromeda's disk, and this subtle gradient in brightness adds to the sense that you are looking at a three-dimensional object rather than a flat projection. The Milky Way band still arcs across the sky in its familiar path, stretching from one horizon to the other and providing a glowing backdrop against which the foreground stars and distant Andromeda both appear. Our own galaxy has not changed substantially during the time that has passed, and the Sun continues orbiting the galactic center in its usual path at a distance of about 26,000 light-years from the core. Earth remains in orbit around the Sun, and the solar system's position within the Milky Way has shifted only slightly despite the passage of nearly 3 billion years. Standing here, under this sky, you can turn your head to look in different directions and see both galaxies at once, one from inside and one from outside. Looking toward the galactic center of the Milky Way, you see the thickest part of the band where the concentration of stars creates a bright region that glows softly in the night. Looking toward Andromeda, you see an external galaxy showing its full spiral structure spread across a large section of sky. The juxtaposition creates a unique view that combines an interior perspective of one galaxy with an exterior view of another, and the comparison helps you understand what the Milky Way itself must look like when viewed from outside. The constellations have changed beyond recognition during the billions of years that have passed since the present day, and the familiar patterns known throughout human history no longer exist in their original forms. Stars have moved through space in their individual orbits around the galactic center, and these motions have shifted the positions of stars relative to each other and relative to Earth. Some stars that were once nearby have moved farther away, while others that were distant have approached. The overall effect is that the detailed patterns of stars visible in the sky have been completely reshuffled. Despite these changes to individual star patterns, the overall character of the night sky remains similar to what earlier observers would recognize, and the Milky Way band still provides the dominant structure across the heavens. The band appears slightly different in detail from how it looked billions of years ago, with some regions brighter and others dimmer due to the shifting positions of star-forming regions and the deaths of massive stars. But the basic nature of the Milky Way as a bright river of combined starlight crossing the sky persists, and this continuity connects the distant future to the deep past. Andromeda's brightness now rivals that of the Milky Way band in terms of the total light contribution to the night sky. And on moonless nights, in dark locations, the galaxy provides enough illumination to very faintly see your surroundings. The light is not strong enough for detailed visibility or for reading, but it creates a subtle glow that is detectable by human eyes adapted to darkness. The galaxy's central region contributes most of this light, and the bright core shines with the combined luminosity of hundreds of billions of stars, concentrated in a relatively small volume. Looking closely at the spiral arms visible in Andromeda's structure, you can identify variations in brightness along the arms that correspond to different types of stellar populations and different stages of star formation. The inner arms appear redder due to the presence of older stars, while the outer arms show more blue-white coloration from young hot stars that formed more recently. The color variations are subtle, requiring careful observation to detect, but they reveal information about the galaxy's star formation history and the distribution of stellar ages across the disk. The approach between the galaxies continues at an accelerating pace, and the velocity has increased from the 110 kilometers per second that characterized the approach in earlier epochs. Gravity becomes stronger as distance decreases, and the acceleration means that the galaxies are falling toward each other faster and faster as they get closer. The current velocity is now several hundred kilometers per second, and this speed will continue to increase as the galaxies move deeper into each other's gravitational wells. The mutual attraction is inexorable, and the collision is now unavoidable, regardless of any other forces that might act. The distance between the galaxies has shrunk to roughly 1 million light-years, or slightly less, and this reduced separation places both systems well within each other's extended dark matter halos. Dark matter makes up the majority of the mass in both galaxies, and the dark matter halos extend far beyond the visible edges of the spiral disks. The halos are already interacting gravitationally, even though the visible disks remain clearly separated, and this interaction influences the orbital paths and the details of how the galaxies will eventually merge. Looking at the sky and thinking about the time until first contact, you realize that only about 1 billion years remain before the galaxies will pass through each other for the first time. On human timescales, this seems impossibly long, but on cosmic timescales, it represents the final approach before a dramatic event. The wait is brief compared to the billions of years that have already elapsed, and the anticipation builds even though the process remains slow and gradual. The sky you see tonight represents the calm before the interactions intensify. The sun continues shining as a main sequence star, and it has been burning hydrogen in its core for billions of years, with billions more years remaining before it exhausts its fuel and evolves into a red giant. Earth has aged considerably, and the geology and climate have changed in ways that would make the planet barely recognizable to observers from the present day. Life may still exist on Earth at this point, but evolutionary processes would have transformed any descendants of current life forms beyond recognition. The night sky they observe, if any observers exist, shows the approaching Andromeda as the dominant feature. The two galaxies share the sky now in a way that highlights their different natures and their impending merger, and looking from one to the other provides a lesson in galactic structure and cosmic dynamics. The Milky Way appears as a band because you are embedded within it, seeing the combined light of billions of stars layered in depth along your line of sight through the disk. Andromeda appears as a complete spiral because you view it from outside, and the external perspective allows you to see its structure whole rather than fragmented into the band-like appearance that internal viewing creates. Both galaxies are spiral galaxies, and they share similar structures despite their size difference, with Andromeda being somewhat larger in both diameter and stellar mass. Both have central bulges containing older stars. Both have spiral arms where new stars form from collapsing gas clouds, and both have extended dark matter halos that provide most of the gravitational mass. The similarities mean that when they merge, they will blend as peers rather than one galaxy simply absorbing the other. And the final result will represent a combination rather than a conquest. The merger will destroy the spiral structures of both galaxies, and this destruction happens through gravitational interactions rather than through physical collisions between stars. When the galaxies pass through each other, the stars themselves will not crash into each other, because the distances between stars are vast compared to stellar sizes. Instead, the gravitational field of each galaxy will distort the other, pulling stars into new orbits and redistributing them throughout a larger volume. The organized rotation that maintains spiral structure will break down into random motions, and the result will be an elliptical galaxy with stars moving in all directions rather than all in one plane. Looking up at Andromeda dominating the sky, you can see the beginning of the end for both spiral galaxies, and the transformation that will reshape them into something completely different. The process will be slow and will take billions of years to complete, but the outcome is certain. The spiral arms that curve so beautifully across Andromeda's disk will be destroyed, and the flat, rotating disk will puff up into a three-dimensional ellipsoidal distribution. The Milky Way will undergo the same transformation, and the night sky you have known throughout this journey will change beyond recognition as the merger progresses. The stars visible in the sky tonight include contributions from both galaxies, even though the two systems remain distinct, and the foreground stars from the Milky Way overlay the view of distant Andromeda without being part of it. Some of these foreground stars are bright and prominent, and they appear scattered across Andromeda's disk. From our perspective, despite being at completely different distances. The separation in depth between our stars and Andromeda stars is enormous, measured in hundreds of thousands or millions of light years. And no confusion between the two populations is possible for observers who understand the scales involved. As time continues to pass and the approach continues, the gravitational effects between the galaxies will begin to manifest in visible ways, and the first signs of tidal interaction will appear in the sky. The next stage of the journey will show these early interactions, the stretching and warping that precedes the actual interpenetration, and the birth of tidal streams that will connect the two galaxies like bridges of stars. The night sky will transform from showing two separate systems to showing the first evidence of their gravitational dance, and the merger will transition from approach to interaction. Hundreds of millions more years have passed, and time has progressed to roughly 3.7 to 3.8 billion years from the present day, placing you at the threshold of first contact between the galaxies. Andromeda now fills an enormous portion of the sky, spanning more than 40 full moon diameters across, and the galaxy appears close enough that its structure shows detail down to individual bright star clusters and dark dust lanes. The approach has continued relentlessly under the pull of mutual gravity, and the distance between the galactic centers has shrunk to about 100,000 light-years, comparable to the diameter of a single large spiral galaxy. Looking at Andromeda's structure, you notice something new that was not present during earlier observations, and the spiral arms no longer appear perfectly smooth and regular in their curves. Warping and distortion have begun to affect the outer regions of the disk, and the arms show slight bends and kinks that reveal the gravitational influence of the Milky Way pulling on Andromeda's structure. The outer edges of the visible disk appear stretched in the direction toward our galaxy, and faint streamers of stars extend beyond the nominal edge of the spiral. These are tidal effects, the result of gravity pulling different parts of the galaxy with different strengths. Turning to look at the Milky Way band across the sky, you see similar distortions affecting our own galaxy's structure, and the band no longer appears as smooth and continuous as it did in earlier epochs. Regions of the band show warps and thickenings where tidal forces from Andromeda have pulled stars outward from their usual positions, and the regular structure that characterized the undisturbed spiral is beginning to break down. The Milky Way is responding to Andromeda's gravitational pull, just as Andromeda responds to the Milky Way's pull, and the mutual interaction is reshaping both systems. The most striking new feature in the sky appears on the darkest nights when the moon is absent and light pollution is minimal, and faint, misty bridges of stars connect the two galaxies across the intervening space. These tidal streams consist of stars that have been pulled from both galaxies by gravitational forces, stretched out into long, narrow formations that follow curved paths through space. The streams are extremely faint, fainter than the faintest parts of the Milky Way band, and seeing them requires dark skies and careful observation. But their presence is unmistakable once you know where to look. Standing here, witnessing the first gravitational interactions between Andromeda and the Milky Way, you are seeing the visible evidence of forces operating across hundreds of thousands of light years of space. Tidal forces arise from differences in gravitational pull across an extended object, and they stretch objects along the line connecting their centers of mass. The side of each galaxy closer to the other feels stronger gravitational pull than the far side, and this difference in force creates the stretching that produces tidal streams and distorts the spiral structures. The tidal streams appear as faint gossamer threads stretched between the two galaxies, and they trace the paths that stars follow as they respond to the complex gravitational environment created by two massive objects approaching each other. Some streams arc from the Milky Way toward Andromeda, while others extend from Andromeda toward our galaxy, and the overall pattern creates a web-like structure connecting the two systems. The streams will grow more prominent as the interaction intensifies, and eventually they will contain billions of stars pulled from both galaxies and redistributed throughout the space between them. Looking closely at Andromeda's central region, you see that the core remains bright and concentrated despite the distortions affecting the outer disk. And the core will persist throughout the merger as one of the most stable components. The core contains hundreds of billions of older stars, orbiting in a dense spherical distribution around the supermassive black hole that sits at the galaxy's center. Andromeda's black hole has a mass roughly 100 to 200 million times the mass of the Sun, and it influences the orbits of stars throughout the central region through its powerful gravitational field. The Milky Way's core is also visible in a different part of the sky, appearing as a bright concentration within the Milky Way band in the direction toward the constellation Sagittarius, as seen from Earth's present-day position. Our galactic center contains a supermassive black hole, designated Sagittarius A star, and this object has a mass of about 4 million solar masses. The black hole is much less massive than Andromeda's central black hole, and when the galaxies eventually merge completely, the two black holes will spiral toward each other and eventually merge into a single larger black hole. The night sky shows both galactic cores simultaneously from Earth's position within the Milky Way, and you can see our core in one direction and Andromeda's core in another direction, separated by a large angle across the sky. The two bright regions mark the centers of mass around which billions of stars orbit, and they represent the gravitational anchors that will eventually combine when the merger completes. The distance between the cores is still large, about 100,000 light-years, but on cosmic scales, this is a close approach, and the gravitational interaction is intensifying rapidly. The velocities involved in the collision have increased to several hundred kilometers per second as the galaxies fall deeper into each other's gravitational wells, and the speed continues to accelerate as the distance decreases. At several hundred kilometers per second, the galaxies are approaching each other at speeds that would carry a spacecraft from Earth to the Moon in less than an hour. These speeds are enormous by human standards, but they remain modest compared to the speed of light, and the galaxies will still take millions of years to complete their first pass through each other. Looking at the overall appearance of the sky, the combination of two massive galaxies at close range creates a scene unlike anything visible in earlier epochs. And the night sky is brighter overall due to the increased concentration of stellar light. The Milky Way band provides light from one direction, Andromeda provides light from another direction, and the tidal streams add faint contributions scattered across the intervening space. The total illumination on moonless nights is noticeably higher than it was before the interaction began, and dark adaptation reveals far more detail than would be possible under the skies of earlier times. The Sun continues its orbit around the Milky Way's center, and the solar system remains stable and undisturbed despite the approaching galaxy and the gravitational interactions underway. The Sun's position lies about 26,000 light-years from the galactic center, which places it safely in the outer regions of the disk, far from the areas experiencing the most intense tidal forces. Earth continues orbiting the Sun in its familiar path, and the gravitational effects from the distant Andromeda Galaxy are far too weak to influence planetary orbits or solar system dynamics. The approach is entering its final phase before first passage, and the time remaining until the galaxies interpenetrate is measured in tens of millions of years, rather than hundreds of millions or billions. On cosmic timescales, this represents the last moments before contact, and the anticipation builds even though the wait remains long by any human measure. The gravitational dance between the galaxies is accelerating toward its first climax, and the distortions visible in the sky will intensify as the galaxies draw closer and their mutual influence strengthens. The tidal streams connecting the two galaxies contain stars that have been pulled from their original orbits and sent on new trajectories through space. And these stars represent the first population to be exchanged between the systems. Some stars, originally part of the Milky Way, now follow paths that will carry them into Andromeda's structure, while some stars, originally part of Andromeda, follow paths toward the Milky Way. The exchange is gradual and involves only a small fraction of each galaxy's total stellar population at this early stage, but it marks the beginning of the blending that will eventually combine both systems completely. Looking at the tidal streams more carefully, you can see that they are not uniform, but show clumpy structure with denser regions where stars have concentrated under their mutual gravity. These concentrations will eventually form tidal dwarf galaxies, small systems containing millions to billions of stars that orbit independently in the space around the merger. Tidal dwarf galaxies are a common byproduct of major galaxy mergers, and they represent a fraction of the material pulled out of the main galaxies during the interaction. Most will eventually merge back into the main system, but some may persist as separate objects for billions of years. The colors visible in different parts of Andromeda's structure provide information about stellar populations and star formation activity, and the spiral arms show bluer colors than the central bulge due to ongoing star formation. Young hot stars shine with blue-white light and dominate the emission from star-forming regions, while older stars in the bulge emit redder light and create the golden glow of the core region. The color variations across Andromeda's disk reveal the galaxy's ongoing evolution and the distribution of stellar ages throughout its structure. As the approach continues and the first passage draws nearer, the gravitational interactions will begin to compress gas clouds in both galaxies, and this compression will trigger new waves of star formation in regions where conditions become suitable for collapse. The compressed gas will cool and fragment into dense cores that then collapse under their own gravity to form new stars, and this process will add to the stellar populations of both galaxies. The star formation triggered by the merger will become much more intense during the actual passage, but the first signs are beginning to appear even now as the tidal forces compress material in the outer regions. Standing under this sky, with tidal streams connecting two massive galaxies and distortions visible in both spiral structures, you are witnessing the moment when approach transitions to interaction and the merger begins in earnest. The next stage will bring the galaxies through each other for the first time, and the sky will transform as the two systems interpenetrate and share the same volume of space. The calm of the approach is ending, and the drama of the merger is beginning. Though even this drama unfolds over millions of years and maintains a stately pace that allows patient observation and gradual understanding. Time has advanced to roughly 4 billion years from the present day, and the first passage of the galaxies through each other is underway, transforming the night sky into something unprecedented in Earth's history. Andromeda no longer appears as a separate disk in one part of the sky, and instead the galaxy has become a surrounding presence as Earth and the Sun pass through Andromeda's outer regions, or as Andromeda's structure passes through our position in space. The separation between the two galaxies has dissolved in the interpenetration, and stars from both systems now occupy the same volume of space. Looking up at the night sky, you see stars in all directions, and some of these stars belong to the Milky Way, while others belong to Andromeda. But distinguishing between them requires knowledge of stellar properties and measurements that are not available to naked eye observation. The overall stellar density in the solar neighborhood has increased noticeably, and you can see more bright stars scattered across the sky than would be visible from an equivalent position in either undisturbed galaxy. The night sky is richer and deeper, with layers of stars at various distances, creating a sense of three-dimensional depth. Two bright concentrations still stand out against the general background of stars, and these mark the cores of the two galaxies, even though the outer structures have interpenetrated completely. The Milky Way's core appears in one direction, glowing as a bright, irregular patch of combined starlight from billions of stars concentrated in the central region. Andromeda's core appears in a completely different direction, separated by a large angle across the sky, and it shines even more brightly due to its greater mass and higher stellar density. The two cores have not yet merged, and they remain distinct entities even as the disks around them pass through each other. Standing here during the first interpenetration, you can think about what is happening in the space around you, and the process is less violent than the word collision might suggest. Stars from both galaxies are passing through the same region, but the space between stars is so vast that actual star-to-star collisions are extraordinarily unlikely. The average distance between stars in a galaxy is several light years, and in the cores where stars are most concentrated, they are still separated by light months. These distances are enormous compared to stellar sizes, and stars are tiny targets in an ocean of empty space. The probability of two stars colliding during a galactic merger is vanishingly small. And computer simulations of galaxy collisions consistently show that stellar collisions are so rare that they can be ignored in the overall dynamics. Billions of stars passing through billions of other stars will result in essentially zero collisions, and the stars simply pass by each other at distances of light years, with no interaction beyond very subtle gravitational influences. This means that Earth and the Sun face no threat from collision with another star, and the solar system continues its orbit undisturbed through the mixed stellar environment. Looking at the Milky Way band, you see that it no longer appears as a continuous river across the sky, and instead, it has fragmented into multiple bright regions, separated by darker gaps where the structure has been disrupted. The tidal forces from Andromeda have pulled the Milky Way's disk apart in places, and the organized rotation that maintained the spiral structure has broken down into more chaotic motions. The band still traces a general path across the sky, but the smooth continuity has been lost, replaced by a more irregular and patchy distribution of light. The spiral structure of both galaxies is dissolving under the gravitational stresses of the interaction, and the beautiful spiral arms that characterized both systems are being pulled apart and redistributed. Stars that were once part of organized spiral arms now follow orbits that are no longer confined to a single plane, and the three-dimensional structure is beginning to emerge as stars move in all directions rather than all rotating in the same sense. The transformation from spiral to elliptical has begun, and although it will take billions of years to complete, the first stages are evident in the sky. Tidal tails extend into space far beyond the main bodies of both galaxies, and on the darkest nights, you can see these faint streamers reaching across vast sections of the sky. The tidal tails contain stars that have been pulled from both galaxies and flung outward by the gravitational interactions, and they stretch for hundreds of thousands of light years in elegant arcs that trace the complex dynamics of the merger. Some material in the tidal tails will eventually fall back and merge with the main system, while other material may escape entirely and form independent structures. The gas clouds present in both galaxies are experiencing very different conditions from the stars, and while stars pass through each other without interaction, gas clouds collide and compress when they meet. Gas is diffuse, but not infinitely so, and when clouds from two galaxies pass through each other, they slow down and transfer momentum through direct collisions. The compression heats the gas and increases its density, and in many regions this compression triggers the collapse that leads to new star formation. Looking across the sky, you can see the evidence of enhanced star formation in the form of bright blue-white regions scattered throughout the merged structure. And these areas glow with the light of newly formed, massive stars. The young stars are hot and luminous, and they shine with blue-white color that contrasts with the older yellow and red stars that make up the bulk of both galaxies' stellar populations. The star formation triggered by the merger is more vigorous than the baseline rate in either galaxy before the interaction, and this enhanced formation marks the beginning of the starburst phase that will peak later in the merger. The passage of the galaxies through each other is not instantaneous, and the interpenetration takes tens of millions of years as the two systems move through each other at velocities of several hundred kilometers per second. During this time, the sky continues to evolve as the relative positions of the galactic cores change, and as more material is exchanged between the systems. Earth and the Sun are carried along on their orbit around the Milky Way's center, and from their perspective, the transition is gradual and continuous rather than sudden. The supermassive black holes at the centers of both galaxies are now separated by distances of tens of thousands of light years, rather than the hundreds of thousands that separated them before first contact. And the black holes are on trajectories that will eventually bring them closer together. The black holes respond to the overall gravitational field of the merging galaxies, and they will spiral inward toward the combined center of mass over the next several billion years. When they finally merge, they will produce gravitational waves that ripple through space-time. But these waves are not detectable without specialized instruments and pose no danger to surrounding stars or planets. Looking toward the future, from this point of maximum interpenetration, you can anticipate what will happen next, and the galaxies will separate temporarily after passing through each other. The orbital motion that brought them together will carry them apart again, and the galaxies will move away from each other over hundreds of millions of years before slowing, stopping, and falling back together for a second pass. The separation will not undo the damage already done to the spiral structures, and both galaxies will remain heavily disrupted throughout the temporary parting. The stellar orbits have been fundamentally altered by the first passage, and stars that were once moving in organized circular or elliptical paths around their galactic centers now follow more complex trajectories that reflect the combined gravitational field of both systems. Some stars have gained energy and moved to higher orbits, while others have lost energy and moved inward toward the cores. The redistribution of orbital energies and angular momenta is one of the key processes that transforms spiral galaxies into elliptical galaxies during mergers, and the first passage has initiated this redistribution. The night sky during this first interpenetration represents the most dramatic phase of the merger so far, and the view combines elements from both galaxies in a way that is unique to this epoch. The two cores remain visible as separate entities. The stellar density is enhanced by the mixing of populations, and the overall structure shows the effects of gravitational disruption on a massive scale. This is a transition state between the approach phase and the later stages, when the galaxies will become more thoroughly blended, and it captures the moment when two separate systems begin to become one. Standing under this sky, with stars from two galaxies surrounding you, and two galactic cores visible in different directions, you are at the heart of one of the universe's most impressive events, and the grand scale of the process contrasts with the safety and stability of Earth's local environment. The merger is gentle on stellar scales, and individual stars and planetary systems remain undisturbed even as the galaxies themselves are transformed. The next stage will bring temporary separation before the final phases of the merger, and the journey will continue through billions more years of cosmic evolution. Several 100 million years have passed since the first interpenetration, and time has advanced to roughly 4.5 to 5 billion years from the present day, as the galaxies separate temporarily after their first passage through each other. The night sky has changed again, and Andromeda's core no longer surrounds you, but instead appears in the distance, receding as the galaxies move apart under the momentum carried over from their first encounter. The two galactic cores now appear in opposite parts of the sky, separated by the maximum angular distance possible, and they shine as bright concentrations, marking the centers of the disrupted systems. Looking at Andromeda's core in one direction, you see a bright, irregular glow that extends across several degrees of sky, and the core region contains hundreds of billions of stars, concentrated in a roughly spherical distribution. The core is no longer embedded in a beautiful spiral disk, and instead it sits at the center of a highly disrupted structure, with tidal tails extending in multiple directions and streams of stars scattered throughout the surrounding space. The spiral arms that once defined Andromeda's shape have been destroyed by the gravitational forces of the first passage, and they will never reform. Turning to look in the opposite direction, you see the Milky Way's core appearing as another bright concentration, smaller and less luminous than Andromeda's core, but still prominent against the background stars. Our galactic center has also been disrupted by the passage, and the organized disk structure that characterized the Milky Way for billions of years has been broken apart into irregular streams and clumps. The Milky Way band that arced across the sky throughout earlier epochs no longer exists in its familiar form, replaced by a more chaotic distribution of stellar light. The space between the two receding cores is filled with stars from both galaxies, and the stellar density in the solar neighborhood remains higher than it was before the merger began. Some of these nearby stars originated in the Milky Way and have been scattered into new orbits by the gravitational interactions, while others originated in Andromeda and have been captured into the mixed environment surrounding the Sun. The night sky contains a rich mixture of stellar populations, and distinguishing the origin of individual stars would require detailed spectroscopic analysis beyond what naked eye observation can provide. Standing here during the separation phase, you are witnessing a temporary calm between the two major encounters that will ultimately merge the galaxies completely. The separation is real, and the distance between the galactic cores is increasing as the systems move apart, but the separation is also temporary. Both galaxies remain gravitationally bound to each other, and the mutual attraction ensures that they will eventually fall back together for a second and more direct encounter. The orbital mechanics resemble those of a comet approaching the Sun, swinging around and then receding before returning on another orbit. The velocity of separation is decreasing as the galaxies move apart, and gravity continuously pulls against the motion and slows the recession. The galaxies are climbing out of each other's gravitational wells, and they are converting kinetic energy into gravitational potential energy in the process. Eventually, the separation will reach a maximum distance when all the kinetic energy has been converted to potential energy. And at that point, the galaxies will momentarily stop moving apart before beginning to fall back toward each other. The turnaround point will arrive in several 100 million years. Looking at the tidal tails extending from both galaxies, you see long streams of stars stretching across vast sections of the sky. And these structures trace the paths that material has followed as it was pulled from the main bodies during the interaction. The tidal tails contain billions of stars spread across hundreds of thousands of light years, and they create faint arcs and bridges that connect different parts of the disrupted systems. Some tidal tail material is already falling back toward the cores under gravitational attraction, while other material continues moving outward and may eventually escape entirely. The overall brightness of the night sky remains higher than it was before the merger began, and the increased stellar density in the solar neighborhood contributes more light than the Sun's original location in the undisturbed Milky Way would have provided. The stars visible to the naked eye number in the thousands on clear, dark nights, and their distribution across the sky is more uniform than the concentration along the Milky Way band that characterized earlier epochs. The transformation from a disk galaxy to an elliptical galaxy is well underway, and the stellar distribution reflects the three-dimensional structure that is forming. The disrupted state of both galaxies shows clearly in their lack of organized structure, and neither system retains the spiral morphology that defined them before the merger. The Milky Way no longer appears as a band because the disk has been puffed up and redistributed, and Andromeda no longer shows spiral arms because those features have been pulled apart and scattered. Both galaxies are now irregular in shape, and their forms will continue to evolve as material settles into new configurations over the next several billion years. The final elliptical morphology will emerge gradually from this disrupted intermediate state. The star formation triggered by the first passage continues in regions where gas clouds were compressed during the encounter, and scattered, bright blue-white star clusters mark areas where new massive stars have recently formed. These young stellar populations add their light to the overall glow of the merged system, and they contribute to the increased brightness visible in the night sky. The star formation rate is elevated above the baseline levels that characterized either galaxy before the merger, but it has not yet reached the peak intensity that will arrive during the second passage when the cores interact more closely. Looking at the Sun's position within the merged system, you can think about where the solar system now resides in relation to the galactic structures. And the Sun is probably in the outer regions of the combined mass distribution. The Sun's original orbit around the Milky Way center carried it in a roughly circular path at a distance of about 26,000 light-years from the core, and the gravitational perturbations from the merger have likely altered that orbit somewhat. The Sunday may now follow a more elliptical path, and its average distance from the center of mass may have changed by thousands of light-years. The changes to the Sun's orbit have minimal effect on Earth and the solar system, and planetary orbits remain stable despite the galactic scale disruption happening around them. The gravitational forces from distant galactic structures are far too weak to influence the Sun-Earth system or the orbits of the other planets. And the solar system continues functioning as it has for billions of years. Earth's sky shows the dramatic changes to the galactic environment, but Earth itself remains a stable platform for observing those changes. The separation phase will last roughly 1 billion years from this point, before the galaxies reach their maximum separation and begin falling back together. And during this time, the night sky will evolve slowly as the cores continue to recede and as material redistributes itself throughout the merged structure. The separation provides a pause in the merger process, a period when the most dramatic interactions have temporarily ceased and the systems adjust to the new configurations imposed by the first passage. The pause is temporary, and the second approach will bring renewed interaction and will lead directly to the final core merger. Looking toward the future from this point of maximum separation, you can anticipate that the second encounter will be more direct and will involve a deeper interpenetration than the first passage. The orbital energy has been partially dissipated during the first encounter through dynamical friction and tidal interactions, and the remaining angular momentum is lower than it was initially. This means that the galaxies will approach each other more head-on during the second pass, and the cores will come much closer together than they did during the first encounter. The time until the second approach begins will pass gradually, measured in hundreds of millions of years, and the sky will continue showing two separated galactic cores with a mixed stellar population distributed throughout the space between them. The tidal tails will slowly evolve as stars within them respond to the gravitational field of the combined system, and some material will fall back toward the cores, while other material drifts farther outward. The overall structure will remain disrupted and irregular, showing none of the organized morphology that characterized the spiral galaxies before the merger. Standing under this sky, with two galactic cores visible in opposite directions, and stars from both galaxies mixed together in the solar neighborhood, you are experiencing the temporary calm between two storms. The first passage has transformed both galaxies beyond recognition, and the second passage will complete the transformation by bringing the cores together and initiating the final merger. The journey continues through cosmic time, and the sky will continue to evolve as the merger progresses toward its ultimate conclusion. The night sky of this epoch represents a unique state in the merger process, and it will never be repeated exactly as conditions continue to change. The combination of separated cores, disrupted structures, and mixed stellar populations creates a view that is transitional and temporary, lasting only for the billion years or so between the first and second passages. Observers in this epoch witness a galaxy merger in progress, and they see their cosmic environment in a state of transformation that bridges the past and future configurations of the system. Time has advanced to roughly 5.5 to 6 billion years from the present day, and the temporary separation has ended as the galaxies slow their recession, stop, and begin falling back toward each other for the second encounter. The night sky shows both galactic cores growing larger and brighter as the approach accelerates, and the distance between them decreases steadily as gravity pulls the systems together with increasing force. The velocity of approach builds from zero at the turnaround point to hundreds of kilometers per second and continues to increase as the galaxies fall deeper into their mutual gravitational well. Looking at the approaching cores, you see two bright, irregular concentrations of starlight that are converging across the sky, and the paths they follow will bring them much closer together during this second passage than they came during the first encounter. The orbital angular momentum has been reduced, through the energy dissipated during the first passage, and the approach is now more direct and less tangential. The cores will pass within tens of thousands of light years of each other, rather than the larger separation that characterized the first passage. And this closer approach will lead to stronger gravitational interactions. The disrupted structures of both galaxies remain visible as irregular distributions of stars surrounding the bright cores, and the tidal tails that formed during the first passage are now being pulled back toward the main bodies as gravity reasserts its influence. Material that was flung outward during the first encounter is falling back inward, and the tidal streams are reversing their motion and converging on the cores. The overall appearance of the merged system shows material streaming inward from all directions, creating a complex and dynamic structure that reflects the gravitational forces at work. Standing here, watching the second approach, you can see that the stellar density in the solar neighborhood continues to increase as more stars from both galaxies mix together in the same volume of space. The night sky is filled with visible stars scattered across all directions, and the concentration of stellar light creates a brighter overall illumination than was present during earlier epochs or during the separation phase. Some stars are close enough that they appear noticeably brighter than typical stars, and a few might be within just a few light years of the Sun. The gas clouds in both galaxies are being compressed again as the systems approach, and this compression triggers new waves of star formation throughout the merged structure. The colliding gas clouds lose energy through direct interactions, and they slow down and accumulate in regions where multiple streams converge. The accumulated gas reaches higher densities than it had before the compression, and in many regions, the density exceeds the threshold required for gravitational collapse. New stars begin forming in these compressed regions, and the star formation rate increases above the levels seen during the separation phase. Looking across the sky, you can see the evidence of enhanced star formation in scattered bright regions that glow with blue-white light from newly formed massive stars. These star-forming regions appear as irregular patches distributed throughout the merged structure, and they mark areas where gas compression has been particularly effective at triggering collapse. The young massive stars that form in these regions are extraordinarily luminous, shining with millions of times the Sun's light output. And they dominate the emission from their surroundings, despite being relatively few in number. The approach is accelerating toward the moment when the cores will pass each other at close range, and the gravitational interaction between the cores will be intense due to their enormous masses concentrated in relatively small volumes. Each core contains hundreds of billions of stars plus a supermassive black hole at its very center, and the combined gravitational field creates strong tidal forces that will reshape both cores during the close passage. Stars in the cores will be redistributed, and some will gain enough energy to escape the cores entirely and join the outer regions of the merged system. The supermassive black holes at the centers of both galaxies are now separated by distances measured in tens of thousands of light years, rather than the millions of light years that separated them before the merger began, and the black holes are on trajectories that will bring them into the same region of space. The Milky Way's black hole has a mass of about 4 million solar masses, while Andromeda's black hole has a mass roughly 100 to 200 million solar masses. The size difference means that Andromeda's black hole will dominate the final merged black hole's properties. Looking at the overall structure of the merging system, you see that the distinction between two separate galaxies is becoming less clear, and the merged system is beginning to resemble a single object, rather than two interacting objects. The cores remain distinct, but the outer regions have blended together completely, and the stellar populations are thoroughly mixed throughout most of the volume. The transformation from two spiral galaxies to one elliptical galaxy is entering its final phase, and the second passage will complete the core merger that finalizes the process. The velocity of the approaching cores continues to increase as the distance decreases, and by the time the cores reach their closest approach, they will be moving at speeds exceeding 1,000 kilometers per second relative to each other. At these velocities, the passage will be rapid despite the enormous distances involved, and the cores will swing past each other in just a few million years. The gravitational perturbations during the close passage will inject energy into stellar orbits throughout both cores, and this energy injection will puff up the cores and redistribute their stars over a larger volume. The night sky shows the convergence clearly, and the two bright cores are approaching each other across the heavens, like two clouds of light on a collision course. The space between them is filled with stars and gas from both systems, and tidal streams connect the cores with faint bridges that trace the gravitational field lines. The overall brightness of the sky continues to increase as the cores grow closer, and as more young massive stars form in the compressed gas regions, and the illumination on moonless nights approaches levels that allow you to see your surroundings with reasonable clarity. Standing here in the final stages of the approach before the second passage, you can think about what will happen when the cores merge, and the process will create the central region of the new galaxy that will emerge from the merger. The cores will not collide in the sense of physically crashing together, and instead they will interpenetrate just as the outer disks did during the first passage. Stars from both cores will pass through each other with minimal risk of collision, and the cores will merge through gravitational interactions rather than through physical contact. The gravitational forces during the core passage will be complex and intense, and computer simulations of galaxy mergers show that core passages often involve multiple close approaches before the final merger is complete. The cores may swing past each other several times, each passage extracting more orbital energy and bringing them closer together, until finally they spiral in and merge into a single core. The process takes hundreds of millions of years, and the sky will continue evolving throughout this extended period as the cores dance their way toward combination. Looking at the star formation occurring throughout the merging system, you can see that the merger is triggering a burst of stellar birth that will add billions of new stars to the combined population. The compressed gas clouds are collapsing and fragmenting into dense cores that then form individual stars, or star clusters. And this process is happening simultaneously in hundreds or thousands of locations scattered across the merged structure. The star formation rate has increased by factors of 10 to 100 compared to the baseline rates in either galaxy before the merger. And this elevated rate defines the starburst phase. The blue-white color of the young massive stars contrasts with the redder colors of the older stellar populations that make up the bulk of both galaxies. And the color distribution across the sky reflects the mix of ages and populations present in the merged system. The cores appear redder because they contain primarily old stars that formed billions of years ago, while the star-forming regions appear bluer because they contain young, hot stars that formed recently. The overall color of the merged galaxy is intermediate, reflecting the combination of old and new stellar populations. The second approach is bringing the merger to its climax, and the next stage will show the cores merging and the starburst reaching its peak intensity as gas compression maximizes throughout the system. The night sky will transform again as the two cores combine into one, and as the burst of star formation lights up the merged galaxy with the brilliance of billions of newly formed, massive stars. The journey through the merger continues, and the most dramatic transformations lie just ahead. Time has advanced to approximately 6 to 7 billion years from the present day, and the cores of both galaxies are now merging in the process that will create the central region of the new combined galaxy. The night sky shows a single bright concentration in one direction rather than two separated cores. And this concentration marks the location where billions of stars from both galactic centers are mingling in the same region of space. The merger of the cores is a gradual process that unfolds over millions of years, and what you see in the sky represents one moment in this extended transition. Looking at the merged core region, you see an irregular bright glow that extends across a substantial portion of the sky, and the brightness rivals or exceeds that of the full moon due to the enormous concentration of stars in a relatively small volume. The core contains hundreds of billions of stars from both the Milky Way's central bulge and Andromeda's much larger bulge, and these stars are now distributed throughout a roughly spherical region that will form the heart of the new elliptical galaxy. The light from so many stars combined creates a soft, diffuse glow that is clearly visible even from Earth's position in the outer regions of the merged system. The supermassive black holes from both galaxies are now within the same general region of space, separated by distances that have shrunk to thousands of light years rather than tens of thousands. The black holes are spiraling toward each other under the influence of dynamical friction, which is the process by which a massive object moving through a distribution of lighter objects loses energy and momentum through gravitational interactions. As the black holes move through the dense stellar environment of the merged core, they interact gravitationally with surrounding stars and gradually lose orbital energy, causing their orbits to decay and bringing them closer together. Standing here, watching the core merger, you are witnessing the formation of the new galaxy's gravitational center. And all the stars in the merged system will eventually settle into orbits around this combined core. The Sun's orbit has already been altered by the merger, and it now follows a path around the center of mass of the combined system rather than around the Milky Way's original core. The Sun is probably located somewhere in the outer regions of the new galaxy, at distances of 50,000 to 100,000 light-years from the merged core And from this position, the core appears as a bright glow in one part of the sky. Looking around at the rest of the night sky, you see stars distributed in all directions with varying densities, and the distribution lacks the organized structure that characterized the spiral galaxy you started with billions of years ago. The Milky Way band no longer exists because the disk structure has been completely disrupted and redistributed into a three-dimensional ellipsoidal shape. Stars move in orbits that are oriented at all angles rather than being confined to a single plane, and this random orientation of orbits is the defining characteristic of elliptical galaxies. The stellar density varies across the sky depending on which direction you look, and the density is highest when you look toward the merged core and lowest when you look away from it. This density gradient creates a visual effect where one part of the sky appears crowded with stars, while the opposite part appears relatively sparse, and the gradient reflects the ellipsoidal distribution of stellar mass around the galactic center. The overall shape is not perfectly spherical, but rather elongated in one direction, creating the football-like form typical of elliptical galaxies. The night sky is noticeably brighter than it was during earlier epochs or even during the separation phase, and the increased brightness comes from multiple sources, including the concentrated light from the merged core, the enhanced stellar density in the solar neighborhood, and the young massive stars formed during the starburst. On moonless nights, the sky provides enough illumination to see basic shapes and outlines, and the combination of light from billions of stars creates a soft glow that is unlike anything visible from either original galaxy before the merger. The merger of the supermassive black holes is proceeding through the final stages of in-spiral, and the black holes will eventually reach separations measured in light months or light weeks before the final merger occurs. When the black holes get close enough, they will begin radiating gravitational waves that carry away orbital energy at an accelerating rate, and the in-spiral will speed up dramatically in the final moments before merger. The gravitational wave emission will be intense, releasing energy equivalent to a significant fraction of the black hole's combined mass, but the waves will propagate outward at the speed of light and will not affect the surrounding stars. Looking at the distribution of stars near the merged core, you can see irregular clumps and streams that reflect the complex dynamics of the merger, and the stellar distribution is not yet fully settled into a smooth configuration. Some regions show higher stellar density than others, and tidal streams from the original galaxies are still visible as coherent structures, even though they are now falling into the merged core. Over the next billion years, these irregularities will smooth out as stars complete many orbits around the core, and as the system reaches a more relaxed state. The star formation triggered by the merger is now at or near its peak intensity, and the starburst phase that began during the second approach is in full swing throughout the merged galaxy. Gas clouds, compressed during the core merger, have reached maximum densities, and new stars are forming at rates that may be 100 times higher than the combined baseline rates of both original galaxies. The sky is filled with bright blue-white star-forming regions scattered across the merged structure, and these regions contribute significantly to the overall brightness visible from Earth. The young, massive stars formed during the starburst are extraordinarily luminous, and a single O-type star can shine with more than 1 million times the sun's light output. These stars dominate the light from star-forming regions, despite being relatively rare, and they create the intense blue-white glow that characterizes active starburst galaxies. The stars are also short-lived, burning their nuclear fuel at such high rates that they will exhaust their cores and explode as supernovae within just a few million years of formation. The starburst phase will therefore be temporary, lasting only a few 100 million years before the gas is exhausted and star formation declines. Standing under this sky, with the merged core glowing brightly in one direction and young star clusters scattered throughout the view, you are experiencing the peak of the merger process, when transformation is most dramatic and when energy input from star formation is maximum. The system is in a highly active state that contrasts with the quieter configurations of stable galaxies. And this activity represents the transition period between the disrupted merger state and the final relaxed elliptical galaxy that will emerge. Looking at the overall structure of the night sky, you can see that the merger has created something fundamentally different from either original galaxy. And the new system combines elements of both while showing characteristics that neither had independently. The total stellar mass is roughly the sum of both original galaxies, approximately 1.2 trillion stars, if you include all the stars formed during the starburst. The spatial distribution is ellipsoidal rather than disk-like, and the stellar orbits are randomized rather than organized. The galaxy has been named Milkomeda, combining the names of the Milky Way and Andromeda to reflect its dual heritage. The Sun and Earth have survived the merger intact, and the solar system continues functioning normally, despite the dramatic changes to the galactic environment around it. The Sunday may now be in a different region of the galaxy than it was originally, possibly farther from the core or in a more eccentric orbit, but these changes have no effect on planetary orbits or conditions on Earth. The night sky has been transformed, but Earth itself remains a stable platform for observing the changes. The merger of the cores marks the point where the two galaxies have become one in the most fundamental sense. And although the system will continue to evolve over the next billion years as it settles into its final configuration, the major transformation is now complete. The spirals have been destroyed, the cores have merged, and the starburst has begun. What remains is the gradual evolution toward a stable elliptical galaxy as star formation declines and as stellar orbits randomize further through ongoing gravitational interactions. Looking toward the future from this point of core merger, you can anticipate that the system will gradually calm as the starburst exhausts the available gas and as stars settle into their final orbits around the merged core. The next stage will show the peak of the starburst and the beginning of the settling process, and the sky will evolve from this active phase to a quieter configuration that will persist for billions of years as the galaxy ages. The journey through the merger is nearing its conclusion, and the final stable state is beginning to take shape. Several 100 million years have passed since the core merger, and time has advanced to roughly 7 to 8 billion years from the present day, as the starburst phase reaches its maximum intensity throughout the merged galaxy. The night sky is brighter than it has been at any previous point in this journey, and the illumination comes from billions of young massive stars scattered across the merged structure in hundreds of active star-forming regions. The overall brightness rivals twilight conditions on Earth, and you can easily see your surroundings on moonless nights under the combined glow from the concentrated starlight. Looking around at the sky, you see bright blue-white patches scattered in all directions, and each patch represents a young star cluster containing thousands to millions of newly formed stars. The clusters appear as extended nebulous regions rather than point sources because many of them are close enough that their spatial extent is visible to the naked eye. The brightest clusters might be only a few thousand light-years from the Sun, and from that distance, a cluster containing 1 million solar masses of young stars creates a patch of light comparable to a small fuzzy disk in the sky. The color of the night sky has shifted noticeably toward the blue end of the spectrum compared to the redder appearance that characterized the pre-merger galaxies, and this color shift reflects the contribution from the young hot stars formed during the starburst. The massive O and B type stars that dominate the light from star-forming regions emit most of their energy in the ultraviolet part of the spectrum, and the portion that extends into the visible range appears blue-white to human eyes. The older stellar populations that make up most of the galaxy's mass still emit redder light, but the young stars are so luminous that they dominate the overall appearance. Standing here during the peak of the starburst, you can think about what is happening throughout the galaxy to create this burst of stellar birth, and the process involves the compression of gas clouds that triggers gravitational collapse and star formation. The merger compressed gas through multiple mechanisms, including direct collisions between clouds from the two galaxies, tidal forces that squeezed gas into dense filaments, and shock waves that propagated through the interstellar medium. The compressed gas cooled and fragmented into dense cores, and these cores then collapsed under their own gravity to form new stars. The star formation rate in the merged galaxy is approximately 100 to 200 solar masses per year, which represents an increase of roughly 100 times over the combined baseline rates of the Milky Way and Andromeda before the merger. At this rate, the galaxy is forming the equivalent of 100 to 200 Sun-like stars every year, though in reality, the stars form in a range of masses, with most being smaller than the Sun and a few being much larger. The massive stars are rare but dominate the light output, while the low-mass stars are numerous but contribute little to the visible appearance. Looking at individual star-forming regions in the sky, you can see variations in brightness and color that reflect different stages of star formation and different environmental conditions. Some regions appear very bright and blue, indicating recent formation of massive stars that are now shining with maximum luminosity. Other regions appear dimmer and redder, indicating either older stellar populations or regions where dust obscures the young stars and scatters their light. The diversity of star-forming regions creates a complex and visually rich sky that changes in detail from one part of the heavens to another. The starburst phase is temporary, and it will last only a few 100 million years before the available gas is exhausted or dispersed by the energy input from the young stars. Massive stars inject energy into their surroundings through multiple mechanisms, including stellar winds, radiation pressure, and supernova explosions. These feedback processes heat the surrounding gas and can drive it out of the galaxy entirely, preventing further star formation. The starburst will peak and then decline as feedback becomes more effective and as the remaining gas is consumed or expelled. The merged core region still glows brightly in one part of the sky, and the core now shows a more settled appearance than it did during the initial merger. The stars in the core have completed multiple orbits since the merger, and the initial irregularities have smoothed out into a more uniform distribution. The core contains the combined supermassive black hole that formed when the original black holes from both galaxies merged, and this black hole has a mass of roughly 200 million solar masses, dominated by Andromeda's larger black hole, with a contribution from the Milky Way's smaller black hole. Looking at the stellar density in the solar neighborhood, you see that it remains elevated compared to the pre-merger Milky Way, and several nearby stars are close enough to appear as distinct disks rather than points when observed carefully. A star at a distance of 1 light-year would appear as a tiny disk rather than a perfect point, and you might have a few stars at distances in the 1 to 3 light-year range. These very close stars would appear noticeably brighter than typical stars and would contribute significantly to the illumination of Earth's night sky. The ultraviolet radiation from the young massive stars fills the galaxy and ionizes much of the remaining gas that has not yet formed stars or been expelled, and this ionized gas glows faintly in emission lines that add to the overall light output. The hydrogen alpha emission line, at 656 nanometers, creates a reddish glow in some regions where gas is particularly dense, and this glow is visible as faint red patches scattered across the sky. The combination of blue-white starlight and reddish emission from ionized gas creates a color palette that is unique to starburst galaxies. Standing under this brilliantly lit sky, you can appreciate the transformation that the merger has wrought, and the night sky bears little resemblance to the view from either original galaxy before the merger began. The Milky Way band that dominated the pre-merger sky is completely gone, replaced by a more uniform distribution of starlight that varies in density across the sky, but shows no clear band or concentration except toward the distant core. The familiar constellations have been erased by the passage of billions of years and the disruption of stellar orbits during the merger. The Sun continues shining as a main sequence star, though it is aging, and will exhaust its core hydrogen within the next few billion years. Earth has experienced dramatic changes over the billions of years that have passed since the present day, and the surface conditions would be unrecognizable to observers from earlier epochs. The Sun's increasing luminosity over its lifetime has warmed Earth's surface, and the planet may no longer be habitable for life as we know it. But the night sky remains observable from whatever vantage point exists, on or near Earth, and the transformed galactic environment creates a view unlike anything seen from our current position in time. Looking at the young star clusters scattered across the sky, you can think about their future and most of these clusters will not survive intact for long periods. The massive stars that dominate the cluster's light output will exhaust their fuel within a few million years and explode as supernovae. And these explosions will inject energy into the clusters and may disrupt them entirely. The lower mass stars will survive, but many will escape the clusters and join the general stellar population of the galaxy. Only a fraction of the clusters will remain bound for billions of years and evolve into the globular clusters that orbit the galaxy as satellite systems. The starburst phase represents the most energetic period in the galaxy's evolution, and the energy output from star formation exceeds the baseline energy output of the pre-merger galaxies by large factors. The bolometric luminosity of the galaxy, which is the total energy output across all wavelengths, has increased by factors of 10 to 100 compared to the combined luminosity of the Milky Way and Andromeda before the merger. Most of this increased luminosity comes from the young massive stars and from the dust that absorbs their ultraviolet light and re-radiates it in the infrared. The night sky during the starburst peak will be remembered as the brightest phase in the galaxy's history, and future observers, looking back across billions of years, will identify this epoch as the moment when Milkomeda shone with maximum brilliance. The starburst will fade as gas is exhausted and as feedback processes quench star formation. And the galaxy will enter a post-starburst phase characterized by declining luminosity and reddening color as the massive stars die and only the longer-lived stars remain. The transition from starburst to post-starburst will take several 100 million years, and the sky will gradually dim as the young stars age and die. Looking toward the future, from this point of peak starburst, you can anticipate that the system will gradually settle into a stable configuration as star formation declines and as stellar orbits randomize further through gravitational relaxation. The next stage will show the beginning of this settling process, and the sky will evolve from the brilliant starburst appearance to a quieter configuration dominated by older stellar populations. The merger is essentially complete, and what remains is the gradual aging of the new galaxy as it transitions from active youth to mature old age. Time has advanced to roughly 8 to 9 billion years from the present day, and the starburst phase has ended as the available gas has been exhausted or expelled from the galaxy. The night sky is noticeably dimmer than it was during the peak of the starburst, and the brilliant blue-white star clusters that dominated earlier views have faded as the massive stars exhausted their fuel and died in supernova explosions. The overall brightness has declined to levels more typical of normal elliptical galaxies, and the color has shifted from blue-white back toward yellow and red as the remaining stellar population ages. Looking around at the sky, you see stars distributed in all directions with a concentration toward the merged core region, and the distribution creates the characteristic appearance of an elliptical galaxy viewed from within. The stellar density is highest toward the core and decreases gradually as you look toward regions farther from the center. And this density gradient creates a visual effect where one part of the sky appears crowded with stars while other parts appear relatively sparse. The overall structure is three-dimensional rather than flat, and stars occupy the space around you in all directions, rather than being confined to a plane. The Milky Way band that characterized the pre-merger galaxy is completely gone, and no trace of disk structure remains in the stellar distribution visible from Earth's position. The organized rotation that maintained the flat disk configuration has been replaced by random orbital motions that carry stars in all directions around the galactic core. Some stars move on nearly circular orbits, while others follow highly elliptical paths, and the orbital planes are oriented randomly rather than being aligned. This randomization of orbits is the fundamental characteristic that distinguishes elliptical galaxies from spiral galaxies. Standing here during the post-starburst settling phase, you can think about what has happened to the gas that fueled the intense star formation during the merger. And most of it has been consumed in star formation or expelled from the galaxy by feedback processes. The supernova explosions from massive stars injected enormous amounts of energy into the remaining gas, heating it to millions of degrees and driving it outward in powerful winds. The heated gas expanded beyond the galaxy's gravitational reach and escaped into intergalactic space, carrying away the raw material that would have been needed for continued star formation. The gas that remains in the galaxy is now too hot to collapse and form new stars, and it exists as a diffuse, tenuous medium filling the space between stars. This hot gas emits X-rays that would be detectable with appropriate instruments, but it contributes negligibly to the visible light output of the galaxy. The lack of cool, dense gas means that star formation has essentially ceased, and the galaxy has entered the red and dead phase characteristic of old elliptical galaxies, where all the stars are aging populations and no new stars are being born. Looking at the stellar populations visible in the sky, you see primarily yellow, orange, and red stars that represent long-lived low-mass and intermediate-mass stars that formed either before the merger or during the starburst. The blue-white stars that dominated during the starburst have died, and the remaining population consists of stars that will continue shining for billions of years more. The Sun is among this population if it is still on the main sequence at this point, though it is approaching the end of its hydrogen-burning lifetime and will soon begin evolving toward the red giant phase. The merged core continues to glow as the brightest feature in the sky, and the core region has settled into a stable configuration with stars distributed in a roughly spherical shape around the combined supermassive black hole. The core contains hundreds of billions of stars, and their combined light creates a soft glow that is visible from Earth's position in the outer regions. The core's appearance is smooth and featureless to the naked eye, showing none of the structure or irregularity that characterized it during the merger. The system has reached a relaxed state where further evolution will be gradual and slow. The overall size of the galaxy has increased compared to either original galaxy, and the merged system extends across roughly 200,000 light-years in diameter. The three-dimensional shape is ellipsoidal, elongated along one axis like a football, and the degree of elongation is moderate, with the long axis being roughly twice the length of the short axis. This shape reflects the angular momentum present in the system and the way stars distributed themselves during the merger and subsequent relaxation. Looking at nearby stars, you still see an elevated stellar density compared to the pre-merger Milky Way, and the solar neighborhood contains more stars within a given radius than it did before the merger. Some of these nearby stars are very close, within a light year or two, and they appear brighter than typical stars. The increased stellar density is a permanent feature of the merged galaxy, and it results from the redistribution of stars during the merger that brought some stars closer together, while scattering others to larger distances. Standing under this sky with stars distributed in all directions and the distant core glowing softly, you are witnessing Milkomeda in its mature, stable configuration. The galaxy has completed its transformation from two active spiral galaxies to one passive elliptical galaxy, and the major changes are finished. What remains is the slow aging process as stars continue to evolve and as the galaxy gradually fades over billions of years. The journey through the merger is essentially complete, and the galaxy has reached a configuration that will persist for the remainder of its existence. The night sky lacks the dramatic features that characterized earlier epochs, and there are no bright starburst regions, no visible spiral structure, no Milky Way band arcing overhead. Instead, the sky shows a simple distribution of stars that varies in density across the field of view, but shows no complex structure or patterns. This simplicity reflects the nature of elliptical galaxies, which are structurally simple compared to spirals and show little morphological detail beyond their overall ellipsoidal shapes. The Sun's position in the galaxy is probably in the outer regions or halo, at distances of 50,000 to 100,000 light-years from the core. And from this location, the Sun orbits the galactic center on an elliptical path that may carry it to varying distances over the course of each orbit. The orbital period is measured in hundreds of millions of years, and the Sun has completed many orbits since the merger began billions of years ago. Each orbit carries the Sun through different regions of the galaxy, and the stellar environment changes gradually as the Sun moves through its orbital path. Looking at Earth's condition at this point in time, the planet has aged considerably and may no longer support life as we know it. The Sun's luminosity has increased over its lifetime as it ages on the main sequence, and Earth's surface temperature has risen in response. The oceans may have evaporated, the atmosphere may have been lost to space, and the surface may resemble Venus more than the Earth we know. But regardless of Earth's condition, the night sky remains observable, and the transformed galactic environment creates a view that reflects billions of years of cosmic evolution. The galaxy is now entering a long, quiet phase that will last for many billions of years, and during this time, the stellar population will gradually age, and the overall luminosity will slowly decline. The most massive stars remaining from the starburst era will die over the next few 100 million years, and their deaths will remove the brightest objects from the sky. The intermediate mass stars will age more slowly, and many will evolve into red giants before eventually dying and leaving behind white dwarfs. The lowest mass red dwarf stars will continue shining for trillions of years, far longer than the current age of the universe. Looking toward the very far future from this point of post-starburst settling, you can anticipate that the galaxy will continue to exist as a stable system for many billions of years, slowly dimming as stars age and die. The next stages of the journey will explore this far future as the galaxy ages through billions more years and as the universe itself continues to expand and evolve. The transformation from vibrant youth to mature old age is complete, and what remains is the slow fade toward an ancient configuration that will persist far into cosmic time. Time has advanced to approximately 10 billion years from the present day, and Milkomeda has settled into its final stable configuration as a giant elliptical galaxy. The night sky shows the characteristic appearance of a mature elliptical system viewed from within, with stars distributed in an ellipsoidal pattern around the distant core and no trace remaining of the spiral structures that once defined both original galaxies. The overall brightness has declined from the peak starburst levels, and the sky is now dominated by older stellar populations that emit primarily yellow, orange, and red light. Looking at the galactic core in one part of the sky, you see a bright, irregular glow extending across several degrees that marks the central concentration of stars in the merged system. The core contains hundreds of billions of stars orbiting the combined supermassive black hole, and their collective light creates a luminosity that is easily visible from Earth's position in the outer regions of the galaxy. The core appears smooth and featureless at this scale, showing none of the substructure or irregularities that would require telescopic observation to detect. The central black hole has a mass of approximately 200 million solar masses, and it influences the orbits of stars throughout the core region. The Sun has likely evolved off the main sequence by this point in time, and it may now be a white dwarf surrounded by a planetary nebula, or it may have already passed through that phase and cooled to become a dim stellar remnant. The Sun's main sequence lifetime is approximately 10 billion years, and that limit has been reached or exceeded at this epoch. Earth's fate depends on what happened during the Sun's red giant phase, which would have occurred roughly 5 billion years after the present day. The Sun's expansion during that phase may have engulfed Earth entirely, or Earth may have survived as a dead world orbiting the white dwarf remnant. Standing under this sky and looking around at the distribution of stars, you see variations in stellar density that create the sense of structure, even though no organized patterns exist. The density is highest toward the core and decreases as you look toward directions away from the center, and this gradient is smooth and continuous rather than showing sharp boundaries. Some regions of sky contain more visible stars than others, simply due to random variations in the stellar distribution, and these variations create a mottled appearance that changes depending on which direction you face. The total stellar mass of Milkomeda is approximately 1.2 trillion solar masses, including all the stars formed during the starburst phase. And this mass makes it one of the larger galaxies in the local group of galaxies. Most other members of the local group have likely merged with Milkomeda by this point, including the Triangulum Galaxy and various smaller dwarf galaxies that once orbited the Milky Way and Andromeda. The mergers with these smaller systems added their stars to Milkomeda's population and increased the total mass slightly beyond what the Milky Way and Andromeda contributed alone. Looking at the overall shape of the galaxy from Earth's position, you can infer the three-dimensional structure from the distribution of stars across the sky, and the elongated, ellipsoidal shape is apparent in the way stellar density varies with direction. The galaxy is roughly 200,000 light-years across along its long axis, and perhaps 100,000 light-years across along its short axis. And these dimensions make it comparable in size to the largest elliptical galaxies observed in the present-day universe. The shape is stable and will persist for billions of years, barring any future major mergers with other galaxies. The stellar populations in Milkomeda are now dominated by old stars that formed either before the merger or during the starburst phase billions of years ago. And these stars are gradually aging and evolving through their late stages. Stars with masses above about 0.8 solar masses have already died or are approaching the ends of their main sequence lifetimes, while stars with lower masses continue burning hydrogen in their cores and will do so for trillions of years more. The night sky shows primarily these long-lived stars, and the overall color reflects their cooler surface temperatures. The stellar remnants from dead stars are scattered throughout the galaxy, and white dwarfs, neutron stars, and stellar mass black holes contribute to the total mass, even though most are too dim to see. White dwarfs are the most common remnants, formed from stars that had initial masses below about 8 solar masses, and they slowly cool over billions of years while emitting gradually decreasing amounts of light. Neutron stars and black holes formed from more massive stars, and they are generally invisible unless they are accreting matter from nearby companions or emitting in wavelengths that require instruments to detect. Looking at the night sky from Earth's position, you see thousands of stars visible to the naked eye on clear, dark nights, and their distribution reflects the overall structure of the galaxy, rather than showing patterns that would resemble constellations. The random orbital motions of stars mean that any constellation-like patterns visible at this epoch are temporary and will dissolve over time as stars move through their orbits. The familiar constellations known throughout human history dissolved billions of years ago, and no new permanent patterns have formed to replace them. The space between galaxies is vast and growing larger due to cosmic expansion driven by dark energy, and the galaxies beyond the local group have receded far from Milkomeda over the billions of years that have passed. The universe is now much larger than it was at earlier epochs, and the observable universe contains regions that are tens of billions of light-years away. But most of that universe is invisible from Earth, because the expansion has carried distant regions beyond the cosmic horizon, where their light can no longer reach us. The visible universe in the far future consists mainly of the gravitationally bound local group structures that have merged to form Milkomeda. Standing under this sky, 10 billion years from the present, you are witnessing a galaxy that has matured and stabilized after the dramatic transformations of the merger. Milkomeda is now a classic giant elliptical galaxy, containing over 1 trillion stars distributed in a three-dimensional ellipsoidal configuration. And it will remain in this stable state for many billions of years as the stellar population gradually ages. The merger that created Milkomeda is ancient history by this point, and the galaxy shows no signs of its violent past, except in the detailed stellar populations and the structure visible through careful analysis. The overall brightness of the galaxy has declined from the starburst peak by factors of 10 or more, and the decline will continue as more stars age and die over the coming billions of years. The most luminous stars remaining are probably red giants, stars that have exhausted their core hydrogen and expanded to large sizes while their outer layers cool. These giants contribute significantly to the total light output, despite being relatively few in number, and they create the orange-red tint visible in the overall color of the night sky. Looking toward the very far future from this stable configuration, you can think about what will happen as the galaxy continues to age through tens of billions more years. And the evolution will be one of gradual dimming and reddening as stellar populations age further. The intermediate mass stars will die and leave white dwarfs, and the overall luminosity will decrease as these bright stars are removed from the population. Eventually, only the lowest mass red dwarfs will remain shining, and the galaxy will fade to a fraction of its current brightness. The journey continues forward through cosmic time toward that ancient future. Time has advanced to approximately 20 to 30 billion years from the present day, and Milkomeda has aged considerably since the merger completed billions of years ago. The night sky is noticeably dimmer than it was during earlier epochs, and the overall brightness reflects the aging stellar population that dominates the galaxy at this late stage. Most of the stars that were bright and luminous during earlier times have exhausted their fuel and died, leaving behind white dwarfs, neutron stars, or black holes. The remaining visible stars are primarily red dwarfs, low-mass stars that burn their hydrogen fuel very slowly and can continue shining for trillions of years. Looking at the sky, you see that the number of bright stars has decreased substantially compared to earlier epochs, and the stars that remain visible are generally red or orange in color due to their low surface temperatures. The blue and white stars that once populated the night sky have all died because such stars have short lifespans measured in millions to hundreds of millions of years. Even yellow stars, like the original Sun, are gone, having evolved through their red giant phases and left behind white dwarf remnants. The night sky is dominated by the faint red glow of low-mass stars that continue their patient burning. The galactic core still appears as a bright concentration in one part of the sky, but it is dimmer than it was billions of years ago as the stellar population ages and the most luminous stars die. The core contains primarily old stars and stellar remnants, including billions of white dwarfs that contribute little light despite their numbers. The combined supermassive black hole at the very center continues to exist, and it may occasionally accrete matter from nearby stars or gas clouds. But such events are rare at this late stage when little gas remains in the galaxy. Standing under this dimmer sky, you can think about the stellar evolution that has transformed the galaxy's appearance over the 20 billion years since the merger completed. Stars with masses above about 0.8 solar masses have all evolved off the main sequence and died leaving remnants behind. The Sun, if it was one solar mass initially, died roughly 15 billion years ago after exhausting its core hydrogen, expanding into a red giant, and then shedding its outer layers to leave a white dwarf. That white dwarf has been cooling ever since, and it now emits only faint light in the red and infrared portions of the spectrum. The white dwarfs, scattered throughout the galaxy, are gradually cooling toward the theoretical black dwarf state, where they no longer emit visible light, but the cooling process takes tens to hundreds of billions of years. At this epoch, 20 to 30 billion years from the present, white dwarfs are still warm enough to emit some light, and they contribute to the overall glow of the galaxy, even though they are much dimmer than main sequence stars. The oldest white dwarfs have cooled to temperatures around 3,000 to 5,000 Kelvin, and they emit red light similar to very cool red dwarf stars. Looking at the overall stellar density in the solar neighborhood, you see that it has decreased somewhat compared to earlier post-merger epochs, because some stars have been scattered to larger distances through gravitational interactions over billions of years. The process called evaporation gradually removes stars from the galaxy, and occasionally a star gains enough energy through encounters with other stars to exceed escape velocity and leave the galaxy entirely. These escaped stars join the intergalactic medium and become isolated objects wandering through the void between galaxies. The night sky shows scattered red and orange stars distributed across the heavens, with a concentration toward the galactic core, and the distribution retains the ellipsoidal pattern characteristic of elliptical galaxies. The number of visible stars is perhaps a few hundred to a few thousand on the darkest nights, substantially fewer than the thousands to tens of thousands that would have been visible during earlier epochs. The dimming reflects the death of bright stars and the dominance of faint red dwarfs in the remaining population. The universe itself has continued to expand over the billions of years that have passed, and the cosmic expansion, driven by dark energy, has accelerated throughout this time. Galaxies beyond the local group have receded far beyond the cosmic horizon, and they are now completely invisible regardless of how powerful a telescope might be used to observe them. The observable universe from Earth's position contains primarily the merged remnants of the local group, with Milkomeda as the dominant structure, and perhaps a few small satellite galaxies orbiting at large distances. The cosmic microwave background radiation has cooled as the universe expanded, and its temperature is now far below the 2.7 Kelvin value characteristic of the present day. The radiation has been redshifted to longer wavelengths by the expansion, and it now resides in the far infrared or even microwave portions of the spectrum, at temperatures measured in millikelvins. The CMB is effectively undetectable without extremely sensitive instruments, and it contributes negligibly to the thermal environment of the galaxy or the universe at large. Standing under this ancient sky with only the faintest red stars visible, and the galactic core a dim glow on the horizon, you are witnessing Milkomeda in its middle age, well past the vigorous youth of the merger and starburst, but not yet in the extreme old age that will arrive trillions of years from now. The galaxy is stable and will remain so for many billions more years, gradually dimming as the stellar population continues to age. The changes from this point forward will be slow and subtle, measured in billions of years rather than millions. Looking at the stellar remnants that now dominate the galaxy's mass, you can think about their ultimate fates over the extremely long timescales that lie ahead. White dwarfs will continue cooling for tens of billions more years before becoming black dwarfs, theoretical objects that emit no light at all. Neutron stars and stellar mass black holes will persist indefinitely in their current states, barring any interactions that might alter them. The supermassive black hole at the galactic center will slowly grow through occasional accretion and through mergers with any smaller black holes that spiral in. But these events are rare and the growth rate is minimal. The galaxy has become a quiet place by this epoch, and the dramatic events of the merger are ancient history, separated from the present by 20 billion years or more. The transformation from two spiral galaxies to one elliptical galaxy is complete, and the subsequent evolution has been one of gradual aging and dimming rather than sudden change. The night sky reflects this quiet old age, showing faint stars scattered across a dark background, with little to distinguish one region from another, except the distant core's soft glow. Looking toward the even more distant future, from this point, you can anticipate that the galaxy will continue its slow fade over trillions of years as the remaining red dwarfs exhaust their fuel and as white dwarfs cool to invisibility. The universe will become progressively darker and emptier as stars die and as cosmic expansion carries matter farther apart. The ultimate fate involves a cold, dark universe where isolated stellar remnants drift through space, separated by vast distances. But that fate lies inconceivably far in the future. The journey continues toward that distant endpoint. Time has advanced to 100 billion years or more from the present day, and the universe has aged to a point where most stars have died and the night sky has become profoundly dark. Milkomeda still exists as a gravitationally bound system, but the galaxy emits only a tiny fraction of the light it produced during earlier epochs. The stars that remain shining are primarily the longest-lived red dwarfs, faint, cool stars with masses below half the sun's mass that can continue burning hydrogen for trillions of years. These stars provide the only significant visible light in the galaxy, and they appear as dim red points scattered across the dark sky. Looking up from Earth's position, if Earth still exists in any recognizable form at this extreme future time, you see a sky that is almost completely dark, except for the faintest scattering of red stars. The galactic core is barely visible as a very faint, irregular glow in one direction, and this glow comes from the remaining red dwarfs in the central region, combined with very faint emission from cooling white dwarfs. The overall brightness of the night sky is far less than starlight on even the darkest present-day Earth nights, and the darkness is profound and nearly absolute. The stellar population of Milkomeda now consists primarily of stellar remnants, including white dwarfs, neutron stars, and black holes, with only a small fraction of the original stellar mass still burning fuel in active stars. The white dwarfs have cooled over the tens of billions of years that have passed, and the oldest ones emit almost no visible light at all. The theoretical black dwarf state is being approached by these ancient white dwarfs as they radiate away their remaining thermal energy into the surrounding space. The neutron stars and stellar mass black holes contribute no visible light and are essentially invisible except through their gravitational effects. Standing under this profoundly dark sky, you can think about the journey through cosmic time that has brought the galaxy from its vibrant youth through the dramatic merger to this quiet ancient state. The Milky Way and Andromeda, that once existed as separate spiral galaxies, are now long gone, merged and transformed into the elliptical Milkomeda billions of years ago. The stars that populated those original galaxies have aged and died, and their remnants drift through the galaxy on orbits that will continue for trillions more years. The transformation is complete and irreversible. The universe itself has expanded enormously over the 100 billion years that have passed, and the cosmic expansion, driven by dark energy, has accelerated throughout this time. The galaxies that were visible from Earth during the present day have receded far beyond any possible horizon, and their light can no longer reach Milkomeda, regardless of the expansion history. The observable universe at this late epoch contains only the gravitationally bound structures that formed the local group, and even these may have dispersed somewhat through evaporation and the occasional escape of stars or stellar remnants. The cosmic microwave background radiation has cooled to temperatures measured in tiny fractions of a Kelvin, and it exists as an incredibly faint glow in the far infrared or radio portions of the spectrum. The universe is approaching a state where radiation is negligible and where matter dominates the energy content, though the matter is distributed so sparsely that interactions are extraordinarily rare. The universe has become a cold, dark place where isolated stellar remnants drift through vast empty spaces, separated by distances that continue to grow as expansion proceeds. Looking at the few remaining visible stars scattered across the sky, you see that they are all very faint and red, and they represent the tail end of stellar evolution for the longest-lived stars. The red dwarfs that remain active will continue shining for trillions more years before they too exhaust their hydrogen fuel and fade into white dwarfs, or perhaps directly into helium white dwarfs, depending on their exact masses. When the last red dwarf dies, the galaxy will enter a truly dark age, where no normal stars shine and only stellar remnants remain. The supermassive black hole at the galactic center continues to exist, and it has likely grown somewhat over the billions of years through occasional accretion and through mergers with stellar mass black holes that spiraled in. The black hole's mass may now be slightly larger than the 200 million solar masses it had during earlier epochs. But the growth has been minimal because little matter remains in forms that can be accreted. The black hole sits at the gravitational center of the galaxy, and stellar remnants orbit around it on paths that will continue for inconceivable spans of time. The journey through the Milkomeda merger that began billions of years ago, with Andromeda appearing larger in Earth's sky, has reached its conclusion in this far future epoch where the galaxy has aged beyond recognition. The night sky has transformed from the familiar Milky Way band through the dramatic displays during the merger to the bright starburst phase, and finally to this profoundly dark state where only the faintest stars remain. The progression reflects the life cycle of galaxies and the inevitable aging of stellar populations over cosmic time. Standing under this dark sky in the extreme far future, you can reflect on the journey and appreciate the vast timescales involved in galactic evolution. The merger of two massive galaxies took billions of years to complete, and the subsequent aging has taken tens of billions more years. The changes were gradual and continuous rather than sudden, unfolding over spans of time that dwarf human history and even geological timescales on Earth. The universe operates with patient inevitability on these vast scales. The far future ahead from this point involves even longer timescales, and the ultimate fate of stellar remnants involves processes that take trillions to googles of years. White dwarfs will eventually cool to near absolute zero and become black dwarfs. Neutron stars may decay through processes we do not fully understand, and even black holes will eventually evaporate through Hawking radiation on timescales of 10 to the 100 years or more. But these processes lie so far in the future that they are difficult to comprehend, and they extend beyond the journey we have followed through the merger and aging of Milkomeda. The transformation of the night sky from the present day through the merger to this far future represents one of the great stories of cosmic evolution. And understanding this transformation helps us appreciate our place in the universe's vast expanse of time. The Milky Way we see in our current night sky is temporary, destined to merge with Andromeda in a few billion years and to transform into something completely different. The night sky we know is just one moment in a long progression that extends from the past into the distant future. Looking back across the timeline from this far future vantage point, you can see the entire arc of the merger and its aftermath. The approach phase lasted billions of years. As Andromeda grew larger in the sky, the interaction phase involved multiple passages and core merger over several billion more years. The starburst phase illuminated the merged galaxy brilliantly for hundreds of millions of years, and the long aging phase has dimmed the galaxy over tens of billions of years to reach this dark state. Each phase followed inevitably from the laws of physics, governing gravity, stellar evolution, and cosmic expansion. The journey through the Milkomeda merger ends here in this far future dark sky, where the last faint red stars shine against the profound darkness, and where the galaxy exists as a collection of stellar remnants bound together by gravity. The merger that seemed so dramatic during its active phases is now ancient history, and the galaxy has aged into a quiet, stable configuration that will persist for trillions of years more. The night sky tells the story of cosmic evolution, and understanding that story helps us see our own time as one chapter in a much longer narrative. The universe continues its expansion, driven by dark energy that will carry structures farther apart over the coming eons. Milkomeda remains bound together by gravity, resisting the expansion on local scales, and the galaxy will persist as a coherent structure long after the rest of the universe has faded from view. The far future is dark and quiet, but it is also peaceful, showing the universe in a state of maximum entropy, where change has slowed to imperceptible rates. The journey from vibrant youth to ancient old age is complete, and the final state has been reached, stable and enduring across the vast reaches of time.